Is this making this bigger? Nice. Okay. So we're going to continue talking about stress, right? Normal stress, which is an average stress. It's the stress that comes from an area that is perpendicular to an applied load, right? So if we had a force in a member, right, the normal stress is going to be the stress over the area that's perpendicular to that force that's in that member. And so we went through an example, right, a couple examples. This being our second example where we just had a series of different size bars coming from a fixed support. At the ends of each of these bars, we had a different amount of loading. Our first approach here, right, figuring out, we were asked to find the normal stress in each one of these bars. The process to do that would be to start with a free body diagram, right, like we always do. We're trying to find internal forces, and that's what free body diagrams allow us to do. We need to get the F over the A. They gave us the A. So we went through and we calculated what the normal force was, right? The force in each of these bars with 3 free body diagrams. Essentially cutting, right, a free body out of this system of bars that allows us to calculate what that internal force was, right? F, F1, F2, and F3. So now once we have that, I think I have the wrong one here. We're going to start with that, okay? That's the completed one. Once we have that, okay, I'm going to plot a diagram of what is the internal force, right? Is it in compression or is it in tension as we move from one end of the force of the system to the other? So if this was our bar, complete bar length, right? If we started out at F3, right? The far end of our bar, we determined before we had 42 kilonewtons of compression. Then as we moved to the left, we had 6 kilonewtons of compression. And then finally we had 66 kilonewtons of compression. So everywhere along this bar, we know that the force is acting towards the surface of the bars, right? Squishing it against the support. So if we start way out here, right, that 42 kilonewtons is going to do something like this. We're going to get negative 42 kilonewtons. Then as we get to the intersection between bars 2 and 3, right, we have these 2 Q loads that are applying really a tension, right? They're positive or outward from the face of our bars, which is going to reduce our compression that was induced from our R force. So we're going to actually go down to 6 kilonewtons. Or 6 kilonewtons of compression. And then finally, we pass our 2 P loads. Right? Well, the 2 P loads, those are pushing towards the surface of our bars, right? We're going to be squishing bar 1 a little bit more based on these 2 Ps. So we're going to go back down. And we're going to go back down to our 66 kilonewtons that we calculated. Do something like that, right? Negative 66 kilonewtons. So that would be our internal force diagram, if you will. Just kind of a visualization of what's going on in each of our 3 bars as we move from the far right to the far left. Well, now that we have our internal forces, we're given the cross-section dimension, right? B1, 2, and 3 of our 3 bars. We know that they told us they were square. So it's B squared would be the area of each of our bars. We know if we looked out on D2L or in the appendix of the text, right? In our big equations appendice, right? The normal stress or average stress is sigma equals F over A, right? Force over an area that's perpendicular to that force. So we can run through and merely plug and chug each one of these. So if we went to bar 1 to begin with, right? This is bar 1, bar 2, and bar 3. We're going to start with 66 kilonewtons. We're going to divide that by 60 millimeters squared, right? We're going to square that because it's a square bar. We get negative 66 kilonewtons over now 3,600 millimeters squared. This is where, as I mentioned the last couple times we've met, you got to continue with your units, right? Make sure you keep track of your units. We know that stress has a unit of pressure, right? Force over an area, so pounds per square inch, right? We talked about this idea of pascals, a Newton per meter squared, right? Well, now we have kilonewtons over millimeters squared. So I'm going to change our kilonewtons into newtons. So we have 1,000 newtons per kilonewton. You can divide that by 3,600 millimeters squared because, 1 million newtons per meter squared equals 1 megapascal equals 1 Newton per millimeter squared, right? There's 1,000 millimeters in a meter. And if you square that, that means that there's a million millimeters squared per meter squared. So 1 Newton per millimeter squared is essentially 1,000,000 newtons per meter squared, which is 1 megapascal. And we'll use that unit frequently in this class just because you'd end up with a lot of pascals. You just get a lot of zeros out there because it's not a very large measure of stress. So with that being the case, if we run this out, we get negative 18.3 newtons per millimeter squared, or as I just mentioned, that's a pascal. Or megapascal, sorry. So we can just do that, follow that through for all of our 3 bars. F2 over A2, we get negative 6 kilonewtons over 400 millimeters squared. I'm going to multiply by 1,000 newtons per kilonewton, and we get negative 15 megapascals. Lastly, we have the stress in the third rod. We have 42 kilonewtons divided by 1,600 millimeters squared times 1,000, negative 26.3 megapascals. Does that all make sense? All right. 400 millimeters squared. Our rod was 20 millimeters on each dimension. We have 40 millimeters for our other rod. Okay. That's normal stress, right? So the stress in a cross section, right? That has to do with the normal force and the area that's perpendicular to that, right? That would be normal stress. Any questions? All right, we're going to talk about bearing stress, which is a variation of normal stress, okay? We've got these 3 blocks here, right? These are just composites. What they're depicting is you can see the depression, right? Circular depression. This is a bolt hole, and this would be a washer underneath a bolt. And then if you put a nut on both sides, nut and washer on both sides, and then you just squeeze to this composite, right? So in this picture here, right, in this picture here, you got a little bit of an indentation of your washer, right? Then you got a little bit more, and then we nearly blew through the entire material, right, on the third one. bearing stress is a special case of normal stress. Generally, compression where two surfaces interact. Right, so where the washer is contacting this material, right, there's a normal force there. And that normal force is acting over an area, right? That intersection between the washer and the material, right, has a cross-sectional area. And that area is perpendicular to the applied force, right? If you're tightening up that bolt is squeezing that material, inducing a force on the material, and that force is resisted across an area, right? The area of the washer on our composite or a 2x4, something like that, right? And so that area is perpendicular to that force. So we end up getting basically a normal stress that's acting between those two materials, right? The washer and the wood, or two pieces of wood. Okay. This would be this is our washer on a composite. Okay. Well, we can have quite a few different types of bearing stress behavior, okay? This one's probably the most common or easy to wrap your head around. This is a washer in which you had a bearing failure, okay? And this had to do with, well, you can't see it here, but trying to find one here. Nothing really, but so this would be a washer or some piece of metal that has a hole for a bolt, right? So then you put a bolt through this hole, and whatever you're putting the bolt through, right, that bolt is getting pulled down with something, right? Some sort of load. And so that bolt is bearing on the side of this hole, right? So this bolt bared so hard on this washer, right, on this steel, that it actually deformed the edge of the hole, right? And so that bolt, as it's pushing along the side of the hole, right, bears on this metal. And so there's a bearing stress there, right? We've got a normal force, right, a force that's induced by the bolt onto the plate. And then there's a cross-sectional area here, right, that's normal to that force that's trying to resist it. So you end up getting a normal stress or bearing stress between the bolt and the plate, okay? So this would be a bolted connection. Okay. So as mentioned, bearing is very similar, or basically is normal stress. So as we know, the equation for normal stress is force over area, right? And that force is perpendicular to the area in which we're calculating. Right, so we have area in bearing essentially is what we need for our denominator. That's our perpendicular area. So in our case for the washer, right, on our wood surface, that bearing area is the contact area, right, between the washer and the wood. So if we were looking at area bearing, it would be this guy right here. Right, it's all of that area there is our bearing area. That's the area that's perpendicular to the applied force, which is the squeezing force that you would apply from a bolt. The bolted connection is a little bit different. In that our bearing area is the area right? The edge of our plate area, that bolt is contacting the plate.
Don't want that. So these are our bearing area. Right, where this is just our contact area of our washer. Right. In principle, it's a normal stress. Can't stress that enough, the fact that it's the area that's perpendicular to the applied force, right? That's how you would get your bearing area. For our bolted connection there, right? If we were to cut our cross section, crossed our bolt hole, something like this. Okay. Our bearing area is not the circumference, right? It's not the length of the arc, right? The hole, because we know that normal stress is the area that's perpendicular to the applied force. So our applied force is coming down like this, right? And so we need to know what the perpendicular area is to that applied force. And so we're really looking at if this was our diameter D, and this was the thickness of our plate T, that bearing area then becomes D times T, right? Because as the bolt is looking at the plate as it's bearing on it, right, it only is going to see the width of the hole D and the thickness of the plate T, right? As we know from normal stress, we're looking at the area that's perpendicular to the applied force, right? This was our applied force. That perpendicular area, or our bearing area, is the thickness of the bolt or width of the hole times the thickness of the plate. Right, we would call this the projected contact area. Of the bolt on the side wall of the bolt hole. Okay. So as mentioned, to determine our bearing stress, we need our applied force and our contact area. All right. And as you can imagine, this is a very, very big simplification of the real world, right? Assuming that the bolt, right, if your bolt was a lot smaller than your hole, that contact area is not going to be as nice and projected as we would see here, right? It's not going to bear on all edges of that bolt hole, right? It would if your bolt's the same size, but as you get that bolt smaller and smaller, right, your contact area gets smaller, so the idea that we would just use the projected area of the bolt in the bolt hole becomes a lot of it simplified, right? The real world does something like this, right, where you would get some very, very large stress concentrations right where the bolt is contacting the plate originally.
This is a finite element model. You guys will likely run into this, especially the METs, as you guys continue on if you haven't already. SolidWorks. This is ANSYS. But SolidWorks is a program that I'm sure some of you have maybe had some experience with, but if not, you probably will in your time here, okay? But an incredibly powerful tool that essentially allows you to model a real world situation, okay? As close as you can, so you can get closer results and actual stresses, right? So this would be real world. It's more complicated. But if you were doing some back of the envelope sort of calculations, just trying to get a feel for things, right? Our projection method here for bearing area would work just fine, right? You can imagine for like our bearing of our washer, if you had, say, a bolt that was 1 inch in diameter and the washer was 18 inches in diameter, right? And the bolt is applying the force that the washer is resisting, right? Through bearing on, say, this wood surface, that washer would have to be really thick in order to spread that load out uniformly, right? Because that washer will start to deform and it won't be pushing as hard on the very outside edges as it would where that bolt is contacting the washer. So again, there's some simplifications in this process, but in general, it gets us really close. All right, so that would be normal stress, bearing stress, okay? Now we have shear stress. All right, so we've looked at stress that is perpendicular, right, to an area. Now we're going to look at stress that's parallel to an area, right? So normal stress was intensity of a force, right, to an area that's perpendicular to the applied force. Well, now we're looking at shear stress, which is the intensity of the force parallel to the internal force. That's not right. Yes, it is. Yeah. Okay. Intensity of the force parallel to the internal force. So with normal stress, if we look back at our sign convention, we had 2 blocks. We would have positive normal stress, right? If our force or stress was acting away from the surface, we would have negative if our force or stress was acting towards the surface. If we looked at these 2 little blocks, right, and we were to be pulling on them, we're going to stretch them, deform them. This block would look something like this eventually, where it actually gets a little bit thinner. Or it would squish out, right? If we compressed something in a block of steel, it would start to bulge out. If we looked at a block of steel and we started pulling it apart, it would actually start to get thinner. This is all based on a Poisson's ratio, which we'll talk about later on in the class. But this relates our deformation perpendicular to the applied load. You can imagine you're not getting rid of any material, right? So as you stretch something and make it longer in one direction, the volume has to stay the same. Well, if the volume stays the same, it's going to have to get thinner in the perpendicular direction, right? Same with if you compressed something, you're making one dimension smaller. Well, it's going to be squished outward in a perpendicular direction, okay? If we look at shear stress, right? So now we had normal stress, which is perpendicular to the surface. Well, now our force is going to be parallel to our surfaces. So if we look at a couple blocks here now, we apply shear stress to them. We're going to have positive and negative signs, right? As we always do. Positive shear stress essentially takes our square and makes it into a rhombus or an equilateral quadrilateral. Does something like this, right? So the way I remember it is up and to the right, right? Up and to the right is positive, up and to the left is negative. Right, it's going to deform our shape up and to the right or up and to the left, right? The forces are acting towards one of those corners. So that's how I've imprinted it in memory, okay? So a positive shear stress is going to create a rhombus looking something like this, right? A negative shear stress is going to create a rhombus looking something like that. Up and to the left. Well, what does this equation look like? Well, we know stress is force over an area, right? It's a pressure. So we have pounds per square inch. So the force that we're going to be dealing with when we're looking for the direct shear stress again, we're going to be calculating an average stress like we did with normal stress. In this case, it's denoted as V over A sub V, or our shear force, which we would call V, over our surface area over which shear is distributed, or A sub V. And so what's the area in which that shear force acts over? All right, this is the same as saying the force due to shear over the area due to shear. So V is force applied in shear. All right, you remember some of this from the eGen 203, right? You guys went through some beams, moment shear diagram, so we get shear forces. A sub V is surface area over which shear is distributed. Right. And these are parallel to one another. Right? Our applied force V is parallel to the area in which that force acts. Yes?
What's like, can you give us an example of shear? Like, what would be shear?
So shear would be like, well, this one would be two boards glued to one another, and we try and pull them apart, right? So as that force is trying to move from one end of the system to the other, it's got to run through this joint, right? So there's going to be a shear force along that joint, and then there's going to be an area over which that joint acts, right? Another really common one is bolts, right? A lot of times we put bolts in shear, like this bolt that's in this plate,
right? We bolted through this plate, and we were hanging on that bolt, right? That force that's applied in the bolt has to then pass through into the plate, and it's shearing that, trying to shear that bolt off, right? So it's got a shear force in it, and so it's gonna have a shear stress in it because it's got an area of the bolt in which that shear force acts, right? And they're acting in the same direction. We're gonna go through a couple examples here, which hopefully will make a little more sense. Okay. One thing to note though here before we continue is that again, the real world is fairly complicated, okay? In this case though, we're making the assumption, like we did with normal stress, that we're calculating an average stress here. We're assuming that the stress acts evenly over the entire cross section, the area in which we're dividing by. So we'll say we will assume tau, or shear stress, is even over our contact area. Okay. So we'll do a couple examples here. Shear stress. Okay. So this would be the testing that you would do in order to test, say, the adhesive properties or shear strength capabilities of glues, right, or adhesives. Glulam beams, if you guys walked over to American Indian Hall, there's tons of glulam beams. Glulam beams are a wood product that's made by taking dimensional lumber, right, like 2x4s, 2x6s, 2x8s, okay, and gluing them on top of one another, and you create a very large member out of them, right? You take like 10 2x4s, stack them on top of each other, right, and you'd have a 15-inch tall beam by 3.5 inches wide. Used a lot of times in, you know, residential construction, commercial construction. Okay, American Indian Hall has a lot of them. If you walked in there and looked in the entryway, you'd see a bunch of them. Okay. Well, we'll deal with why those need to be glued together later on in the class. But a lot of times they do testing of those joints to make sure that as they glue and lap each of those 2x4s on top of each other, they have enough strength in order to get the composite behavior that somebody wants, right? When we lay those 2x4s out and stack them up, it makes the beam stronger, it makes it taller, increases our moment of inertia, areas, a lot of the material properties. And so what they'll do is take those two pieces of wood, right, 2-dimensional pieces of lumber that they would plan on gluing together. They would create a joint in which they would know the area, the cross-sectional area. In this case, we're going to say the joint is 4 inches long and 3 inches wide. Okay. So it's 4 inches long, 3 inches wide. We have our test specimen sitting in our test machine. Okay. I think METs have one of these over in EPS, but CETs and CEs, we have the testing lab, which is in the first floor of Cobley. There's a testing machine just like this. It's got clamps in it. You can clamp something in it, pull on it, and see exactly what the failure loads of things are. CETs, you'll have a class in which you get to break a bunch of stuff in the labs. Okay, should be fun. So we have two wood specimens. They're connected via this adhesive lap joint. And this testing machine then decides, right, we decide that we're going to exert 65 pounds on this lap joint. And we want to find our average shear stress of our glued joint, right? How much shear stress do we have across that surface, right? Well, if our solution is the average shear stress, we know that our average shear stress is our shear force divided by the area in which that shear force acts.
Any ideas where we would start, knowing that this is where we're ending up, right? We need tau. It's like we started any other problem. How did we start some of the other problems? Free body diagram, exactly. Thank you. One of these times I'm going to train you to say free body diagram. The free body diagram is not going to be the right answer, but hopefully. So we get a free body diagram. Well, what am I going to do? I'm going to cut out a free body, which is the premise of a free body diagram. The free body that I'm going to cut out of this real world situation is essentially cutting above and below this lap joint. Also going to cut it on it, put it on its side so it doesn't take up a whole lot of space. Well, in a testing machine, generally, the way this works is that one of the heads or the apparatus that fixes our wood specimen or whatever specimen we're testing is actually fixed in space, it's sitting there. And then the other one is a part of an actuator, and it's the one that ends up moving up and down. So the one that's moving is the one that's exerting the force, right? So we're going to assume one side of this, as we decided, 65 pounds. And then we're going to have a fixed end of our apparatus, right? That's restraining or holding back this specimen from moving when the other head decides to move, right? So we need our dimensions. We got 4 inches long is what we were told. We know that this is 3 inches wide. That's generally our free body diagram, right? Well, we want to know what F is. Well, I think it's fairly straightforward at this point, right? We have one equation, sum of the forces in the X. Can't forget our coordinates here, right? I'm going to say positive to the right. We have positive to the right, and we know that sum of the forces in the X have to equal to 0. Well, F is positive. It's acting in the direction we assumed is positive in our free body diagram. 65 pounds acts in the opposite direction. Well, that's pretty straightforward. F now equals 65 pounds, right? And the fact that F is positive from this equation means that we guessed F in the right direction, right? So that is truly the direction of the force on the other side, right? So we have 65 pounds to the left on the right, on the left side, 65 pounds to the right on the right side. Well, now we know what V is, right? Because that force has to make its way across this joint and down to the other side. So we really have this shear force acting across that lap joint of 65 pounds. So we've got tau equals V over AV equals 65 pounds over 12 inches squared. Well, that is our 3 inches times our 4 inches. Right, that's the cross section of the area that's parallel to our applied force. Right? We wouldn't want to use the cross section of one of these wood plates, right? Which would be the thickness times the width. We want the area that's parallel to our applied force, or the area of the lap joint itself. So pounds per square inch, 5.4 psi. Any questions on how we got there? Okay. We're going to go to another example. As I mentioned, bolts are a very common element that undergo shear stress and shear forces. If you go to the engineering building, the new one, Norm Asbjornsen, okay? If you walked up on the
third floor and you look up and there's a little clear story. There's a section of the building that's another story higher than the third story, okay? In there, there's a bunch of diagonal braces, big metal rods that are going back and forth, crisscross, across that opening, okay? At the ends of all of those metal rods are what we would call a clevis, okay? It's essentially a connection component that goes into a yoke, right? Big Y section, and allows you to bolt through that yoke into a steel plate. The reason those cross members are in that building is in an earthquake, we need to be able to transfer forces from one area of the roof to the other side of the roof. So that's what those rods are all for, is to do that. So in an earthquake or big wind event, okay, those rods are in tension, okay? So we got these big P forces potentially acting through that clevis, right, to connect the rod to the other side of our opening. So in this case, an example of which we have a clevis connection is loaded by an external force P of 150 pounds. And they give us the clevis bolt diameter is 5/8 of an inch. Based on this, they want us to find, you might guess this, right? The shear stress in our bolt. Well, we know our shear stress, right? Tau average equals shear force divided by the area over which the shear acts, or the area that's parallel to that applied force. So we're going to start this out. How do we start it? Free body diagram, right? We need to know what our shear forces are, right? What's acting in our bolt, the shear force in our bolt. In order to do that, I'm going to cut out a free body diagram. So I'm going to cut this clevis just as the yoke turns into two pieces, right? Above and below this plate. So I'm going to cut this right here. I want to know what force is traveling through this bolt. Okay, that force is going to be in our clevis, right, in our top and bottom section of our clevis. So I'm going to cut it so I can isolate that force and calculate what that is. So we're going to start by drawing this guy up. Say this is our top of our clevis. This is our steel plate. This is our bottom clevis. Looks something like that. We also have a bolt, right? That's extending through the entire length. Does something like this. We need some coordinates because we have a free body diagram and our forces become vector, right? They have direction, not only a magnitude, but a direction, which influences signs when we're calculating what those forces are. We're going to have applied forces, right? Ones that we know and ones that we don't know. What we do know is there's a force P that's acting on this plate, right? It's up there. They tell us that that P is 150 pounds. Well, if we have P acting in the other direction, this clevis is symmetrical, right? So that the line of action of P acting across our entire clevis system, right, is in the same length, same plane. Because it's in the same plane, if there's symmetry there, so you can imagine, this would be P over 2, and this would be P over 2, right, or 75 pounds. Something like that. Sum of the forces in the X equals 0, right? We have 150 pounds acting to the right. We we have 150 pounds acting to the left, right? 75 to 75. This clevis isn't going anywhere. There's no motion. Sum of the forces equals 0. We have equilibrium. Well, as we were looking through our lap joint, right, in the last example, we had this shear interface, right, where the forces had to travel through the connection. Well, in this case, if we have P over 2 acting on that top portion of the clevis, well, that P over 2, right, has to travel through this connection now and come out through the steel plate. Same with this P over 2, has to work its way through the connection, make its way out of our steel plate. We could also draw this free body diagram. Now that we know that we have our forces acting to the left, we could cut out just this bottom portion of the clevis, right? Basically, erase all this stuff up here, and we would have to have a force acting through our bolt that made equilibrium possible, right? So we have what we would call a shear plane. In our system. Right, we had a shear plane in the last example also, right? We had one shear plane. In this case, we have two shear planes. Well, if we have two shear planes, that means the force has two locations in which it travels through from one side of our free body diagram to the other. And this allows us, we essentially have two ways of calculating what the shear force is, or shear stress is, right, of our bolt, and we will do that on Wednesday. I'll be assigning homework on Wednesday. It'll be due next Wednesday, which means we'll have a quiz around middle of next week also, which will be on D2L. Make sure you go out there and double check that you can access the text. Okay? Because if you can't access the text, you're not going to be able to access the quiz. The EM Learning Center opens today. All right? There's information out on D2L I posted. Gives you who is going to be essentially at the EM Learning Center for us as eGen 208. Okay? There's times of the week. If you can't make those times, it doesn't work for you, reach out to Dr. Flynn Murray. She'll be able to accommodate that in some way, shape, or form. Okay? Reach out to myself. All right? That's it.